Add fractions. You gotta get a common denominator, right? Okay, so on this one, before you jump into it, this is kind of a trick question a little bit. You can make this pretty easy. Right? You can factor it, but do you even really, I mean, there's a way around this one. Almost the same, aren't they? Ah, okay. Okay. Okay, what'd you run into on this one? What do you think? Okay, yeah, this one, we could factor this, but it's unnecessary, right? We're seeing something here. So if we look at these denominators, negative x squared plus 2, I could rewrite that, right? Isn't that the same thing? Isn't that the same thing as saying negative 1 times, and I could really just put a negative out front. Everybody agree? Okay. So what can I multiply? All I need to do is get a common denominator, right? I don't have to do anything fancy here. I just have to get the denominators to be the same. And my tool for doing that is always the same. I'm going to multiply by 1 in the form of something divided by itself. In other words, I'm going to multiply the top and the bottom by the same thing. So what would I do here? Multiply the top and bottom of, say, the second fraction by what? Negative 1. Right? Now what's that give me? I just get x squared minus 4 over x squared minus 2 times negative 2, not times, plus negative 2 over x squared minus 2. So what's my answer look like there?
Why is it?
Yeah, what's x squared minus 4?
Yeah, you
Oh, whoops, sorry. Should have been.
It's also actually wrong.
You're right. I made mistakes there. So x to the 4th minus 2. There we go. How's that? Okay, so if I add up on the bottom, I'm just going to get my common denominator, right, of x squared minus 2. And then we do what we always do when we're adding up fractions. We're just going to take the sum of the numerators over my common denominator, right? Which gives us x to the 4th minus 4. Okay, so there's my fraction. Now, could I simplify that?
Yeah.
Okay, what could I do to this one? What could I do to the top?
Minus it from the bottom.
Say it again.
I feel like minus it from the bottom, simplify from the bottom, so you'd have x squared minus.
Ah, okay. So I could write the top is, I could write that as a difference of squares, couldn't I? Right? X to the 4th is just x squared squared. Right? Everybody agree? So this stuff right here, I could write that as a difference of squares x squared minus 2 squared. What's that factor into then? What's the difference in squares pattern? Sam, what am I gonna get from that?
X squared plus
Okay, times.
X squared minus.
Okay, and so then we end up with, now look what we got here. But there's one important thing coming. We get x squared plus 2 times x squared minus 2 over x squared minus 2. So if our goal is to write this in simplified form, then can we cancel here? Okay, we can. But remember that if we cancel, we've changed the function now, haven't we? Right? So we've written it in simplest form. The simplest form is x squared plus 2. But if I were to graph, let's say I were to take this solution right here. So this is my function, right? Before I cancel, before I simplified the answer. If I graphed that function and I graphed this function, would they be exactly the same? No. What's going to be the difference? Okay, we filled in some holes, didn't we? Right? Okay, so we have to declare, if we're going to simplify it like this, we have to include the domain also. So we got to kind of backtrack here for a second. We skipped a step at the beginning, and now we got to go back and fill this in. What is the domain of our function?
X can unequal the square root of 2.
Almost. Or negative the square root of 2, right? When we look at the bottom here, we have to, remember, in our domain, we can't include any values of x that would force us to divide by 0, right? So how do we go about doing that? Well, one way we could do it is we could factor the bottom, but this is not a really convenient expression to factor, right? Because we're not going to get integer results, right? So what we could do instead, and we could, I mean, if you think about it, you probably could think of a way to factor that. But instead, we could just ask ourselves, okay, well, what values are going to cause the bottom to be 0, and we'll exclude those values. In fact, we could even do the algebra in kind of an interesting way here. We could say, all right, so we know the bottom consists of the expression x squared minus 2, so the domain is going to have to be such that x squared minus 2 is not equal to 0. It's kind of a weird way to write it, but when we write a not equal to like that, algebra works exactly the same with a not equal to sign as it would with an equal sign. So what are the steps we'd go through here? We can point to a single x, right? So we can isolate it. So what are the steps we'd go through to solve for x? Add 2. And then we'd square root, which means we have to include plus or minus. So x cannot equal plus or minus 2. Square root of 2, sorry. Right? So we'd have to include that with our answer. We'd have to put a comma there, and we'd have to say, okay, that's our answer. That's our simplified form of the function. But keep in mind that x cannot equal the square root of 2, and x cannot equal negative the square root of 2, right? This is a good way to write it, though, because it makes it much, much easier to graph, right? What's that look like? What is that function? It's parabola that's been what? Moved up 2, right? So if we want to graph this thing, it makes it really simple to get a sketch of this graph, right? We're just going to go like so. However, we do have to go back then and say, all right, but square root of 2, so that's about 1.4. So like right there and right there, we've got to add holes to the function, right? But it does make it a lot easier to graph. A lot easier to graph than that thing, right? That's kind of messy. Right? We want to write it in the simplest form, but we still have to include any values of x that are excluded from the domain. Okay? All right. Okay, what would you do with one like this? Let's just look at one sort of problem. Now I'll let you guys work on this stuff. You'll have some questions, I'm sure, but I want to get you going. So what about a situation like this? You got a freight train, averages 30 miles per hour traveling to its destination with full cars and 40 miles per hour on the return trip with empty cars. Find the total time in terms of D. So D is just the total distance, right? The distance, or the distance from one place to the other. Okay. And really, if we can just set this up, it's not like the problem is going to be really hard to do. Any ideas? So the total time is just going to be like the time on one going one way plus the time coming back the other way, right? R is just the rate. So the rates are 30 and 40, right? So what do you think? Any ideas? What's going to be the time going with the full cars to the destination?
X over 30.
Okay, good. Let's call that T1. And that's just going to be D is our distance over 30, right? We'll call T2, the time coming back. What's that?
T over 40.
So then total time is just going to be the sum of those two times, isn't it? Right?
T over 70.
No, can't do that. What would I have to do here to add this up? I've got to get a common denominator. Well, what's my least common denominator going to be? With numbers, it's so much easier. Yeah, the biggest number that
Good job.
the smallest number that these would both go into would just be 120, wouldn't it? Right? And with numbers, we kind of looked at this with numbers yesterday, and you guys are so intuitive with numbers that you don't really have to think about it in terms of breaking it into factors, right? You probably instead, what would your strategy be? Probably just to find multiples of 30 and 40 until they match up, right? Okay, and that's fine. We won't belabor that point. So I would just multiply the first one by what?
4.
4 over 4. Second one we multiply by,
3 over 3.
and there you have it, right? 4D plus 3D is what?
70.
Over 120, so we end up with 7 1/20ths times the distance. Okay, there it is. All right. Why don't you have at it? I'll let you work on this stuff.